without further ado, New York City Category 37, Andrei Rodin. Yeah, this is my 10th time coming or speaking here, and anyways, it's always a pleasure speaking about whatever it says and speaking about.
Thank you so much, Nazan. Thank you for invitation, for everyone coming. So I'm going to speak about Vladimir Voevodsky and his really non-orthodox ideas about mathematical structure, which I think he never published, but he shared. Actually, that is going to be based on our correspondence, just a little piece of that I think it's interesting. But yeah, so this is Vladimir, Volodya.
Very young, huh?
Yes, this is, but so I'm going now, but I begin by giving kind of standard story, kind of received narrative about structures and homotopy type theory, because there are actually rather a significant number of publications, people who really actually saw univalent foundation this as a kind of achievement, as a fulfillment perhaps of this structuralist program. And that, interestingly, was not the way that Volodya actually understood this thing. So I tried to contrast it a little bit, then I provide this little piece of our correspondence, and then actually he gave a historical example. He explained how his ideas about structure using historical examples from commentary to first book of Euclid's Elements produced in 5th century by Neoplatonic philosopher Proclus, which is a very important source actually for all Greek mathematics, the major source indeed. Right, and then I provide some reconstruction. So I actually explain what it has to do with homotopy type theory. I'm pretty sure that that was Volodya's thinking. Of course, responsibility is mine, but here I actually don't have doubt. Then I provide two different interpretation of this, say, analogy. One classical constructive. I think this constructive somehow it's closer to homotopy type theory, and come to some general conclusions. Okay, so the standard story. Of course, I will not try to give definition, really precise definition what is structure. There is many things, but okay, I give again my own standard definition. It actually depends on what we call axiomatic method in this particular form in which it's emerged in the very beginning of 20th century, even officially in the last year of 19th century, 1899, when Hilbert's Foundation of Geometry were first published. So I would say mathematical structure is a model of some set of axioms. So it's really depends on that anatomy, and important thing that criteria of identity for structures, and this is isomorphism. So the idea is that isomorphic structures somehow the same, right? And from here, this idea to make axiomatic theory categorical in the sense which is not related to category theory, but means that all its models are isomorphic. I'm not going to discuss that, but that's somehow idea, right? That a theory would have a single model, but single means a class of isomorphic model, or models are isomorphic. No classical example like groups, but here I think it's still it's standard example. But actually, what is a model of, say, three well-known, I will not repeat, right, the axiom for group theory. And actually it's one particular group. And there is some linguistic thing that if you take book in a normal introduction to group theory, you would have these axioms, definitely, right? But actually it's not, how say, theory, it's not what can be deduced from those axioms alone. Obviously, right? It's rather we may call, we are interested in a kind of model theory of group theory in this specific, in this, how say, logical sense, and that's what we call group theory. Even the notion of, say, subgroup, right, like Lagrange theorems, simple things, they are all involve multiple models. So in that sense, so if it's in set theoretic foundation, they're all supposed to be derivable from axioms of set theory, but not only from axioms of group theory. And for example, in this manifesto of structuralism written by John Dieudonné in I think English publication of 1950, and that was written a little bit before that in French. He confuses these things. He just says, he describes what is axiomatic method, and he says, look, here are axioms, here we may prove, for example, that unit in the group is one unique unit, but that's actually a kind of rare axiom, right? Thing that you really, as mathematician would say, just follows from definition, right? And less trivial thing in group theory, and of course there are many very non-trivial things in group theory, they are not consequences of these three axioms. They concerns how the different models of these axioms relate. So I think it's important. Right. And then we have actually specific notion for isomorphism, for group. And when we talk, we want to have identify structure up to isomorphism. Here we mean specific isomorphism for group. And in a sense, this notion of isomorphism, it follows, it's somehow suggested, I don't know if we can make a really, how to say, formal result here or not, from the axioms, right? So in a sense, the axioms of group theory tells us what isomorphism of this structure is. And still, there is a big, actually, problem to this idea, which I now try to elucidate in this standard setting. Yes?
Does it mean, like, when you say the axioms of a theory dictates, like, the morphisms between those models, do you mean, like, the elementary embedding of the models actually will be a... Like,
no, I'm just talking about group isomorphism, right? It's a map which preserves operation. And since, right, and then how...
but how is it determined? Like, how are isomorphisms determined by set axioms?
Yeah, yeah. I think we may give kind of artificial answer, right? Then whether, I know one example, that if we talking about morphism, general morphism, not isomorphism, right? For example, for topological space, there is no, there is this choice. The morphism could either preserve or reflect the structure. And the choice is for reflect, standard choice, right? What we call continuous map, and not for, and so that somehow seems not to be an axiom. That seems to be further assumption somehow based on practice or whatever.
No, but I think even in case of groups or actually any structure, I think the axioms do not really play much of a role. The axioms are sort of needed to determine classal structures that satisfies it.
Yeah, but now I'll try to explain what is problem. Actually, there was this excellent, great talk by Arnon Avron. I was not here, but I was in audience by Zoom, and he discussed this example of finite ordinals von Neumann and Zermel. Actually, he gave good reason to prefer this one, right? But still, what is actually a problem? Let's just think where this notion of isomorphism comes from, really, in that case, right? And if you look in these things, there is nothing is preserved locally, right? The thing which is preserved kind of globally, just a recursion which is preserved. And so it does not reflect anything like internal structure. And in that sense, actually, it's just like we talked with Sergei before this, and I call it notching numerals, right? Just, what is, yeah.
Hilbertian numerals.
Yeah, and that, by the way, was relatively recent archaeological finding, which, of course, there is part of speculation about that, but it's interesting, if just 1 minute, is consistency number 29. Maybe one may try to gain, why 29? It's not only on that. All similar findings have 20. Yes, yes. And so speculation, of course, is that lunar is a thing that, unlike annular cycle, you can directly observe. So it was the earliest kind of numbering. Yeah, so we actually have the same thing here, right? Yeah. So we have absolutely the same thing. The only thing that if we want to do things set theoretically, we kind of start with the empty set because it's the only set, how say, kind of individual set in existence of which is guaranteed by axioms, right? And so you can, so of course you may invent kind of crazy artificial models which are all standard models here, right? Because we have this idea of numeration, which is standard model, which by the way remains completely intuitive. So in that sense, piano arithmetic does not, how say, help us to distinguish this standard model from other models, or at least my understanding, right? So yes, and there is nothing in these particular sets that make them number 3. Actually, it's not even correct to say that it's just a class of those sets, right? So what really makes a model is a set plus this generator. It's how they're generated. If you kind of abstract away how they generate, you abstract away your model. There is no model, right? Yeah, and problem is that if you just look at your objects, right, you don't really know what, so to speak, belongs to the theory, right? And what are kind of accidental features, so to speak. You don't know that. In the case of arithmetic, we decided just intuitively, by strong intuition of this notches, Hilbert numeral. And say in group theory, what we do, okay, in a sense, as I told, we invent this notion of isomorphism, at least suggested, I put this way, by the axioms. However, we cannot simply replace or make some simple, how say, factor group or quotient, right? It's called quotient construction to identify a class of isomorphic group. Exactly because we don't know exactly what we should pick up and how this notion of isomorphism is working. So yeah, so the difficulty is with we don't know, given the groups, which are properties are group theoretic and which are not, which are artificial, right? We just have some groups. We don't know which properties are group theoretic. We first should somehow, by trial and error, prove that certain, say, properties are invariant under isomorphism, then we kind of include them in group theory. But there is no way to know this beforehand.
So one can raise all kinds of objections to it. So one of them, if you have this isomorphism with a 3-defined set theoretically as something that you have a structure with a relation and another, say, another binary relation, and we know what an isomorphism is, then now, so what this isomorphism does, it preserves not just anything that's axiomatically expressible, but all properties that can be sort of formulated in any kind of logic. So, for example, one property of, if you look at a standard model of arithmetic, take any subset, okay, and it has a least element. So we say every set has a least element. This is not an arithmetic property. This is property of a well-ordered of order type omega, which has nothing to do with arithmetic. So it's very hard to say that this is a particularly arithmetic property, but nevertheless it preserves about every isomorphic, all standard models of arithmetic share that property. So it's not, it wouldn't be quite proper to say that you identify something as an arithmetic property that is preserved under isomorphism. They all are.
No. The argument is, okay, you are looking at this Zermelo and Foy-Neumann.
Oh, no. Okay, so here the argument would be a little different because you look at the representation of the structure, that elements.
Okay, let's talk about groups.
So what elements are made of doesn't really matter in sort of this abstract model theoretic setting. They can be made of anything. However, the point can be made that set theoretically, von Neumann represents the ordinal nature of numbers, While Zermelo is just counting. You just count, and you just have to have sort of discrete set of elements that you can use for counting. But within each next number is the set of numbers before it, and it is represented by von Neumann's representation. So it has some arithmetic, not arithmetic, but ordinal number.
Say the number of elements, right? Is irrelevant because it's different in Zermelo and in a von Neumann case. Exactly. So it's irrelevant. But how you know it's irrelevant?
No. But I'm saying that the von Neumann, all the sort of von Neumann representation of the standard logic arithmetic, all natural numbers, represents this idea. Each next ordinal number is the set of previous, the ordinal characteristics. While the Zermelo doesn't, you just have we need a set of distinct elements that differ. It doesn't matter that they grow even. So but still, what matters is the arithmetic that you defined on it, addition and multiplication, which is nowhere near, and it doesn't really follow. It's a longer discussion.
Yeah, okay. Let's maybe discuss. No, I think here it's actually not so much my original ideas. I think that all was discussed. So Bill Lovier called it wobble about identity. He used this word. I heard from him, right? And actually, all this so-called philosophy of mathematical structuralism, people like Shapiro, Stuart Shapiro, Reznik, and I think, I don't know, Steve Audi, many others, they somehow played on that, right? They say, okay, MacLean, for example, he really, there is this, he talked about infinite cyclic group, and so it's one and not one. I think they, in a sense, even cultivated this ambiguity, because that would make kind of philosophy, give place for philosophy. But what happened with, yes, and as a remark, it's actually in at least standard category theory, we have the same thing. For example, we know that objects we identify up to isomorphism or up to unique isomorphism, like terminal object, and for morphism we shouldn't treat in the same way, right? We should have kind of strict equality or inequality, and so why nobody really knows. There is no strict rules about this. Everything depends on concept, but one may have. That's actually I draw an article by Benedict Arens and what's his name? Page North, very much. They really formulated. One may have this principle, which in philosophy actually we call indiscernibility of identicals, right? That identical things should have the same property. Of course, it's contested. Not you may say I don't know, hungry one time and not hungry, but still it's very basic. It's in a sense more basic than the other way around. Then right? No. I'm not talking about the round. I'm not talking about identity of indiscernible, but indiscernibility of identities, right? And actually, if we want to treat isomorphism that way, if it should resemble somehow identity, it should verify something of that sort, right? That for all the expressible properties, we would share that isomorphic structure would have the same properties, right? And which is not the case like Zermelo and for Neumann, of course. Right, because we have more properties, we have a lot of expressible.
But see, I think it's very anti-structural. In structural approach, you tend not to look at the nature of elements. The structure is defined by functions and relations.
Yeah, but you should somehow know in advance what you should pay attention to and what you don't. And you don't have formal rule about this. This is it, yes.
So, for example, if we take the theorem and apply it to the case of groups, can we say that the size of a group is a structural property?
Size of a group? No. No. If you talk about size, you mean
how many elements?
How many elements? No, it's not a structural property. In that, yes, I mean, a group of different size are different structures, right? But in that sense, right, size is preserved, yes, then yes.
But
it's one of things which is preserved by isomorphism, right? But it's not sufficient, of course. For
okay, so this theorem is just necessary.
It's not a theorem so far. It's how say desiderata. Yes, it's what we want to be good structuralists. right?
Okay, so it's
Can you give an example in group theory of something that's not structured? So, for example, you have two different presentations of a group, okay, and one uses 3 symbols or something like that, and the other one uses 2 symbols. Well, each word can be of different lengths in different ways.
Okay, I should, because everything saying it's introduction so far. Yes, yeah. So in ZF, mathematics is not supported, right? And
I completely object to that claim. I understand that.
yeah. Okay. We may come back.
It's a standard fact about mathematical structure.
Yeah, but the thing is that in univalent foundation, it does work. It is verified. And there in a sense, we don't need to even specify what kind of isomorphism we are talking about. We should not say, okay, for groups we have that, or for rings we have something different. Because here on the other hand, it's works actually not for all structures, but say for almost, I don't know exceptions at least, maybe there are, all familiar structures. And the precise result, those structures called univalent, and they verify, I called it like local univalence axiom, because normal univalence is about types, right? And this is about terms, this local univalence.
One comment, I apologize, it was being recorded. I don't want to interrupt all the time because for me it's so new. Okay, but I just want to say that those statements are not quite precise, but the keyword is the property, right? So so what set theory mathematics offers you that if you have an isomorphism between two structures, then every logical property that one structure has, the other one. But that's Tarskian definition of what a logical property is. So what you prove, for example, introductory or lecture in model theory, that all first-order properties are transferred by isomorphism. That's a fundamental property. But this is, and you have to prove it. But this is a theorem of logic. So logic.
But which isomorphism? Which isomorphism?
Any. The isomorphism.
You mean any?
So say you have two structures, set one binary relation, one binary relation. An isomorphism is a bijection between one and the other that preserves the relation. That's all we need. So, and then the theorem says that every isomorphism of that type preserves all first-order properties. That's a theorem of first-order logic.
Yeah.
But then, what is logic? Logic, Tarski says, is the system that obeys the theorem. So infinitary logics, modal logics, all kinds of logics. We know all reasons what was a logical property satisfies the isomorphism theorem. You prove it by induction or complexity of So I think that this discussion here is not what's theoretical, what's categorical, but what is a property. So in this univalent theory.
Yeah, and I think here is my remark about group theory, that if you are using these results, right, you just have one axiomatic theory, but say in group theory, we are actually not in group theory as axiomatic, we are in set theory. We're in a broader context.
We are never really in group theory. Group theory is just a set of axioms that we use to So what does it apply to? A structure with a binary function. And axioms tell you which of those structures is a group and which one is not. And so there are isomorphisms between, there cannot be an isomorphism between a group and non-group, but isomorphism preserves all axiomatic properties because they are first order.
Okay.
Because I will just make a longer statement and I will not object anymore. But on the previous slide, you said that in set theory something doesn't happen. It happens, but the key word is what is a property.
Yeah.
Then we talk about first order properties, and almost anything is a first order property. But then it also, in Cervello, when he formulated replaced the comprehension axiom, and see what sets exist, that Saltum used that definite property. They talked about what is a definite property. You look at an element of a structure, and a definite property is something for which you can decide whether it has the property or not. So this was like pre-first order logic approach. But now we move to, now the standard is that we have this.
No, that's what I meant. And I think is that in set theory there are more properties and there is no formal criteria which are invariant and which are not.
No, there are anyway.
There is no general theory.
There is very general.
Yes? Okay. But let me. Wait, thanks. Yeah, so that's definition what is univalent category. So we have something like univalence axiom. Standard univalence axiom says that, say, we have identity types, we have equivalence types, and we have a natural map from identities kind of embedding, right, in equivalences. So univalence axiom says that the map is invertible. Just non-constructive, it says, right? And here we have similarly, so we have a identity of terms, type of identity of terms, right? And isomorphism of terms. And then we have similarly canonical map. And for certain categories like groups and all that, it's actually an isomorphism, it's invertible. And so for these categories, this which actually covers quite a lot, we actually do have this equivalence principle. Right. So it looks like it's there is a lot of papers by Steve Audi and other people who, in the very beginning of Univalent Foundation, say, look, wow, that's what we for decades tried to do. And finally, Volodya Voevodsky himself, I found at least one talk where he mentioned that. So it was one of motivation. But interestingly, in later, I think this I have a date which I forgot. Right. In 2006, he gave this general talk, motivations behind in Institute of Advanced Studies, and then he did not mention that. So he mentioned proof checking, verification. He did not speak about this structuralism. But yeah, but anyway, that is the usual view that in this new setting, this old dreams, I call it dreams a little bit ironically, but the idea is that what people somehow talked without having any formal result behind. Okay, Roman, you think that there was a formal result? I know that Mackay invented some theory where he claimed to have exact formal justification for this structuralism, right? For this multi-sorted logic is what he did. But here we got it somehow for free, right? And we don't need special idea of isomorphism for group, for rings. If we do it here, it's automatically, and of course in set theory, just set theoretic rejection, it's just nothing, right? So it's a background, but then, okay, it's not nothing, but but then we have this leap from just set theoretic isomorphism to say group isomorphism to ring isomorphism, and that is leap that makes no. Okay, I'll try to understand. Yeah, maybe I'm wrong, but again, that's not just my argument. It's published many places. I can find this argument. Now,
can I just thank you for not mentioning one word, Voevodsky?
Yeah.
I mean, if you're going to bring up structuralism. And I think a lot of modern mathematics is influenced by that.
Yeah.
You know.
Yeah. Actually, when I mentioned Jean Dieudonné, it was written Nicolas Bourbaki. It was later known that he actually. It is Bourbaki Manifesto, called Architecture of Mathematics. Okay. Now to.
So the beginning of the Bourbaki on set theory.
Yes. So I just quote a little bit from our correspondence. Volodya asks me historical question. So we played a little bit this game. He's a great mathematician, I am kind of historian. Yeah, which was stupid on my part, absolutely, because he actually knew some piece of history better than myself. Yeah. So he asked me, in Proclus, we find a clear distinction between a property and a structure. Okay, see his reflection of how to define an angle in his commentary. Okay, and I'm going to show you what it is. Relation is a joint property of two or more objects. Now that's understandable, right? etc. But next thing, at least I did not understand first, and so I asked him for classification. In philosophy and mathematical logic, the world, whatever it means, is based on a collection of objects and collection of relation between these objects. That is a collection of properties or assemblies of objects. Right? In Russian, he used предметы, like Gegenstand. I translate from Russian. I wonder, Volodya asking, when and how there emerged the strange idea that the foundation of the world can be described as a collection of relation between objects rather than a collection of joint structures on assemblies of objects. And here I did not understand, because, okay, structure is something like objects and relations and objects. And but here he opposes objects relations to structures. And that I did not understand what he meant. Yeah, and then he even, actually I tried to ignore this historical part, which I must confess, did not take seriously. But later I convinced myself that he was, if not completely right, then at least he was on a very interesting historical track. But that's for different talk, I will not. But still he said, there should be a moment when this idea, somehow replacing relation by structures, what he calls by relations, was first presented as an auxiliary simplification. As if something says, let's assume this laughably simplified version of the problem, just like in mathematics, people often consider a simplified version of problem in order to test this or that general idea.
Would you say Tarski was the first?
Right, and then
I said I would have to keep quiet.
and then he adds this.
It's all very relevant, and there is much to say, and I'm not negating. This is a very interesting point of view, but it would have to be a long discussion. And Tarski said he plays a role.
Okay.
I just want to quote Leibniz, who said, everyone knows that continue is not made of points.
Yeah.
Right? And he was right.
That's right.
Yeah.
And we in set theory, of course, how do you make it?
Yeah, but that's
Right,
Wait, I have to
that's
interrupt.
relevant.
We're going out for dinner later.
okay. Yeah, and then he adds actually another point which helped me after all to understand. He says a relation either holds or doesn't hold, right? Straight lines are either parallel or not, but a structure can have more than one representative. And no, at that point I still did not understand. And so, yeah, Proclus, that's already told you, that it's major told. And yes, and historical question actually I'm going to ignore. Right, so I asked him, could you tell me what you call structure after all, right? And then he became a bit official. And he said, yeah, I'm saying, if it's not a set with collection or relation, what it is? Okay, I skip my stupid ideas. And he said, a structure on several objects is an entity that can link these objects in a number of different ways. A relation between two given objects either hold or does not hold. He repeats, a structure is a link such that the set of its possible version have more than one element. No, okay, it's still, and here I understood what he meant, and given Proclus example. So now I'm going to give this Proclus example, okay, and I hope you also understand. Probably some of you already did, you know, homotopy type theory. Yes. Yeah, and then that's also important, noting that given this definition, relation is a special case of structure. So it's not really opposite, it's a special case. Okay? Right. Now, what Proclus? We are back to Euclid. Okay, Euclid has this definition of plane angle in book 1. Plane angle is something he calls inclination. Okay, I will not give you Greek work. I forgot Greek. Of the lines, no matter. Yeah, it's important that it's not necessarily lines are not necessarily straight. They could also be, he called it for example, line and a tangent and part of tangent circle. And he has interesting theorem, for example, that that thing is smaller than any plane angle. You know, things like that. Right. Actually, he has a more than one. Right. That's so next definition, he says what is rectilinear, so exclude such things. On the other hand, then in book, yeah, it's important that it's always smaller than pi, right? So there is no straight angle for Euclid. That's important. Then there are actually other definitions in stereometric, what is a kind of solid angle and so on. But what we don't find there, it's a, say, definition of, like for spherical geometry, for example, right? It's not in Euclid. So we don't have spherical triangles. But actually when Proclus comments, he doesn't care. He actually brings everything he knows about angles. So he's not formalist in that sense. Now what wants Proclus? He's probably, I'm not going to details, just kind of setting. He wants to say either angle is a relation, meaning actually instance of relation between two given lines, like pair of parallel lines or something, or it is a quality. He just follows Aristotelian 10 categories, just picking up 3 as possible candidates. So it's kind of figure like circle, for example. It's a quality of being circle, quality of being an angle, or it's a quantity. Since we can compare and measure angles, it's kind of quantity. Then he says in the end that it's kind of everything at once and they somehow dialectically combine. So I skip this. I'm just taking a small piece on definition 1a, definition of plane angle, where Proclus actually tries to show that it is not a relation. Again, it's important when I say relation is the instance of relation. It's actually what he means. Here there is no room for different interpretations. Right, so what Proclus says, if the angle is an inclination, that is relation, and in general belongs to the class of relations, it will follow that when the inclination is 1, there is one angle and not more. For if the angle is nothing other than a relation between line or between planes, how could there be relation? One relation but many angles, right? So if we have just one instance of relation, it's one thing, okay? But okay, I probably give you first a diagram and ignore the text. He says, look, take a cone, right? So we have a fixed two, how they call it, образующие lines, or A or B, diameter, and now we have a plane angle A or B, and actually two curved lines, right, which just on the surface of the cone. And so he says there is a problem.
Right.
So, conclusion, it's not a relation. And that's the argument that Volodya picked up, and that's what he's going to call a structure. And should I say what it has to do with homotopy type theory, right? Yeah, so in homotopy type theory, no, I think most of people should know, but if not, the idea is that we have, for example, for a given type, which is represented by space, say S, we picking up two terms, T1, T2, and then equality is represented by a path. Right, so we have a type of paths, right? And so to say it's T1 is equal to T2 or not, we should find a path or say there is no path. And of course, that should be all in S, because here we may compare only terms of the same type. But the whole thing of this homotopy thing, that actually we are going to distinguish between different paths up to homotopy, and then we may distinguish say certain paths are homotopic, certain not, and then we can go all the way up to higher homotopies, right? Again, because homotopic means there is a homotopy or no homotopy, right? But we may be interested in kind of individual homotopies up to second homotopy, and that's what actually gives you this, yes. This is, I read that if you would have wormhole in space-time, it actually gives the same effect of gravitational lensing as big mass, right? And that would be kind of physical situation of homotopy. Yes. Now let's, that's actually what he meant, Volodya, right? But, so now let me spend some, I don't know, 10 minutes for a little bit looking at this argument, what actually Proclus says. One thing, first, what it actually does not say, right? Because it's kind of easy, right. That's, of course, you may object that in Euclid there is no this curved angles, right? But it's irrelevant to Proclus. For him, it should work anyway. Right. Of course, if we give a definition, mathematical definition, it's actually not supposed to be to pick up a single object. There are cases like that, like empty set, right? But generally, it may be even empty if you define like something like largest prime, or it may have. So it's you can say the definition is bad because it just does not pick up unique object, right? It's not an objection. So what Proclus says, if you want kind of to say, read him charitably, it's actually a different thing, which I called relational uniqueness, this principle, right? And this says just this, that an instance of binary relation is fully identified when its relata are fully identified, right? So we should assume that, say, lines are identified in some way, and then we may distinguish between case where lines hold that relation, do not hold, but anyway, this instance of relation will be identified. And classically, it just goes back to the idea that given these elements, we may talk about ordered pair, right? Yeah, here is symmetric relation. It seems to be symmetric, this inclination. So we may just go with a non-ordered pair, but generally we need, and by the way, what is interesting, we have the same situation as a Zermelo and even more options because there is like explosion of different way to define in set theory what is ordered pair. I just put 2, but there are more, of course, you may invent how many you want, right? So basically this. Yeah, and then, okay, assume lines are well identified, assume this principle, shows that you have a problem, you have more than one angle with this, and conclude that it's not a relation. But, yeah, but then I actually propose a little bit probably more interesting interpretation, which somehow brings us closer to homotopy type theory via, say, constructive logic, maybe via Martin Löf. So here actually we say, we distinguish between proposition and judgment, and talking about witnesses or proof. So we want explicit, no, I'm scared talking, what is right when, explicit evidence. To pick up explicit evidence and not just saying something true or not true, idealistically say, as I just did, right? Of course, things become kind of circular, but okay, because this is an angle, which after all is evidence or is a witness that lines do have this relation, and this is a bit weird to use a definition, but it's not really my problem. So now this principle will be reformulated that proposition, and this is of course a proposition, right? We're saying X holds this relation R to Y. This is a proposition, and it should have at most one proof. And that's actually what homotopy type theory, say, assumes, even it sounds kind of strange, but I come to this later. So if we assume that, right, we see that should be one instance, but we find more than one instance, more than one witness. So it's not a proposition, so it's not a relation, right? Now, of course, you may say, why single proof? You may have many proofs, but then here comes in place this notion that these people in the hot book, it's actually not Volodya's idea, they called it like mere proposition. So the idea is that to have in a proposition, you kind of ignore differences between truths, between proofs. You're only interested whether exists some proof or no proof.
Truncated.
Truncated, right. Geometrically, they call it truncation. And so you ignore all these higher order structures. No, okay, again, I probably skip this explanation because actually for Volodya, I think that was the key thing in all of this homotopy type theory is this hierarchy of types, right? So kind of on the bottom you have, actually on the bottom it's a bit mysterious, some like point, but then you have propositions with yes and no, with empty set and say singleton, right? And then you have sets. And basically all this classical mathematics just works in these two levels, sets, propositions. While he believed that this setting actually kind of opens new horizons, extending this just two-level structure somehow infinitely. And that's, I think, it's interesting really to discuss. Yeah, actually, I tried to give another example using notion of isomorphism. So given a pair of group, we want to have some witness that the group I isomorphic. Oh, by the way, you probably know, yes, certainly that it is unsolvable. It's not algorithmic, was proved by, truncated, I think by Novikov, yes. That was one of Hilbert problem. Not technically, technical problem was asked by Max Den, of course closer to Hilbert, and that question was solved negatively by Novikov, so this is not computable. Of course, we are talking about finitely presentable groups, right? Having finite generators, so you cannot just given generators, given relations, and to devise an algorithm which for all groups would tell you whether isomorphic or not. But for some classes, it works, and there is still work to define these classes precisely. So let's suppose we are in this kind of good class where it's solvable, and the question is the following. Look, shall we insist or not on this distinguishing between different isomorphisms? Suppose we have this algorithm, right, that just given to object tells us and gives us precise constructive procedure, whether isomorphic or not. Would we have any advantage, what we gain, so to speak, right, if we would distinguish different way to do that, right? We already have one good way to do that, whether we discover something new, talking about different isomorphisms. And answer, I think, is that even if we may have this constructive knowledge, what we don't have here, we don't have this identity condition. So isomorphisms are not objects for us, right? We only have this proposition, yes and no. But if we want to study isomorphism as individual things, then we should, following Quine, like no entity but identity, to make kind of identity condition for them. And that's actually what we don't have, what we lack on this propositional level, and for which we may need to go these levels up. Right. Yes. No. Okay. I coming to my conclusion. So, first question: whether this, you see, it's different kind of thinking, right? What I presented in the beginning. So, so you may say, okay, he just was out of all this philosophy, of course, and he called structure something different. But not exactly, right? Because after all, it's special case. All this classical structure is just special case of this one. So it's certainly relevant. And yes, no, okay. Historical question I leave aside, but there is a theoretical question, right? Whether this reduction to truncation somehow justified epistemologically or not. And of course, if we take, for example, groupoid, it can be represented at the standard structure, right? So we may think about groupoid in this way, right? As we have a different, say, we may have another one, different paths and a way to distinguish homotopic and non-homotopic. But we also may, of course, introduce kind of two sort of things. Saying there are points, there are paths as individual, right? So there are some of them are equal, some not. So it's all, of course, expressible in standard mean. I don't know precise result. Maybe some of you know whether the same apply to like omega groupoids, but perhaps yes, I think intuitively at least, right? Why? Perhaps there are some absolute, I don't know, I didn't try really to prove it accurately, but one may imagine that that kind of reduction works. Well, probably not, so I leave it as actually a research question. But even it works, right? I think for Volodya, that was not, after all, very important, right, this form of reduction. So he believed that anyway, that opens something new, at least in, so to speak, human level, right, because it allows to formalize motif theory and other stuff, which I must say, I don't really understand that. It's kind of natural language for that, right? And the fact that it could be expressible, I don't know, in set theory, that doesn't change much in that sense, right? So actually, I think there is an interesting epistemological, philosophical, if you like, issue, is that, you see, for him, for Volodya, of course, priority was to discover something new, you know. For these people, so it was important to, how say, to say some old thing worked out finally, you know. So, if you like, it's just two different sides of the same coins, right? But so one people say, okay, all this thinking about structures, finally, we know how to do that. But Volodya say, okay, maybe you know how to do that, but it's not what is important that we can do more things. Yes. But here I think it's still, of course, a lot of things to need to be like even simple. And that, by the way, have an interesting kind of practical aspect, because the people in this community of proof verification on proof assistance, right? At a certain point, they became enthusiastic about development foundation. But at least we are talking about this group. Some still are. But Lean somehow distinguished probably financially because they got this lot of money from Microsoft. And actually, not recently, already maybe 10 years, they kind of became very hostile to all that stuff. I personally, I spoke to Kevin Buzzard. No, he's kind of a nice guy.
He's great.
Yeah, he's, but he doesn't like it. So now he got new grant for proving Fermat theorem for
100,
you know,
like 1 million UK pounds.
Yes.
Let me introduce.
No, okay. Let me. I give my maybe. It would be better to have him here, right? And probably Kevin, if you listen to this video, please come and tell what you think. But what I got, he says, okay, I just hire a lot of student postdoc. It will be, and they just formalize. You know, they don't care this. They just, you know, go ahead.
Game.
They just go ahead. But there is some strengthen this argument, because finally, if it compiles in the end, right? You say
Coding monkeys.
right,
Yes.
right.
Absolutely.
But if it compiles, then you, at least my understanding of his argument, then he is in a position to say, okay, I just don't care what is inside. I know in general principle that it is compiles means there is formal proof inside. And after all, I don't care about details of the proof, it works. Yes. And I almost finished, I think.
Finish up, because then one story, it's really important.
So just, so my paper is going to appear, yes, that's stuff about Kevin is not in the paper. Yes, thank you. Yes, please.
Let me just say that there are different levels, and I'm sorry, we're going for hours. Kevin Buzzard and I entered into correspondence about this question when Lean was just beginning, and he said, of course, this homotopy type theory is wonderful and likely the right way to do it. He says, I couldn't get any money, and I couldn't persuade people to learn the stuff before they sat down and said, I'm a monkey now. He said this to me. Now, I shouldn't, it was private correspondence. I shouldn't say this. This is going to go out in the net. But that's okay, because he actually made a YouTube video where he frankly, he confronts this and says, this is all probably much better. Voevodsky's crazy, infinite, uncontrollable, serious tower of things. And he says, but no, I've got to get Lean out. I've got to get money. So I'm not giving away any secrets. But before he did that video, before he wrote it, he said, it's better.
I heard him saying in a video also, it's not what he told me, that, look, these guys, they like 10 years or 15 years, they're doing this stuff, they didn't formalize anything seriously, so it's dead ends.
Well, that may have been what he said to you. He said to me, it's the right way to do it. That's right.
You can always force Lean and put the pot back.
Yeah. Will you come out for dinner with us? Yeah. Okay.
What's the story about formalization with Kepler?
That's different story. Kepler.
Oh, Kepler conjecture. Everybody believes it now, I think.
But is the formalization complete?
Yeah, the general value.
There was a great lecture on it, like 4 years ago.
Yeah.
It uses even more foundations than that.
Yeah.
It uses Isabel